But for today's afternoon session, we will have our first talk by Pierfrancesco Urbani on dynamics of training and inferences. Overparametrized two-layer network.
Okay, so thanks a lot for the very kind invitation. It's really a pleasure to be here. So I'd like to talk about the dynamics of training and inference and generation. And this, of course, is inspired by questions in machine learning and generative AI. And the biology part will be that I'll try to address some of these questions, basically using some models that come from computational neuroscience. And so this talk is divided in two parts. So the first part is mostly based on this work with Andrea Montanari that we published last year in ODEs. And then the second part is heavily based on this preprint that I posted some months ago. And it's actually some extension of models and ideas that I've been developing a lot together with Samantha Fournier. Okay, so if I have to name two central experimental discoveries of modern machine learning, I think that the first one is this paper of Krzyzewski, Skever, and Hinton in 2012, where they basically discovered that if you use overparametrized neural networks, these things can learn features, representation from data via empirical risk minimization and some gradient descent or some stochastic versions of it. And the first example where they showed this is basically deep convolutional neural networks that perform either classification or nonlinear regression tasks. And one of the things that emerged after this paper is that all these networks basically work by learning internal representations that align with the structure of the data. And once you learn this internal representation, well, basically there is a part of the network. It's a kind of readout part where you basically solve the regression problem in a low-dimensional space. So it's really key that these networks learn these internal representations. And this happens in these overparametrized settings. So the second discovery that I think can be traced back to this 2017 paper by the Google team that basically invented transformers is that actually when you learn these features of data, you can use them inside some dynamical systems. So you have some pipeline where you have a dynamical system. And these you can use for generative purposes or networks that can show reasoning or cognitive tasks. And of course, there are two main examples. So the first one are generative models based on score matching. So what they aim to do is basically a sample from some, so they use dynamical systems to sample from a probability distribution. And the most extreme case is the one of large language models, where basically the dynamics is the one of next token prediction. And this is your inference dynamics. And these dynamics can lead to models that are basically able to prove theorems. So it's an emergent behavior. And if you look at the architecture of a transformer deep down, the way in which it uses feature learning is the following. So this is a schematic representation of a transformer block. Well, basically, you learn some features from high-dimensional tokens. These are high-dimensional embeddings of words. And then once you learn the features, well, you can combine them along the chain. And this is done in this attention block to predict the next token. Okay, so and this basically very simple architecture that is trying to infer what is the right next token can lead to some reasoning abilities. Now, so we have these two experimental discoveries. They are largely experimental because we don't understand much about them. So there are two, I think, main questions. So the first one is, and it's related to the first discovery, so it's how it's possible that feature learning can appear in such overparameterized settings. So this is really thoughts with classical statistical learning theory. And I think it really requires to build new foundational principles to understand overfitting and generalization. And the second thing is how can we understand these reasoning or cognitive abilities of this LLM? So this is really a new frontier in science. It's not in classical books of statistical learning theory. It's new phenomenology. And I think that I mean, this is like a Copernican revolution. We are one of the questions that all this is posing is how all this is related to neuroscience, right? So we have a model that is displaying some thinking behavior. We can just decompose it, and this is like really something that never happened before in history. And okay, so these are very broad questions, and one mathematical aspect that makes them hard deep down is the fact that to understand both, you need to understand basically high-dimensional nonlinear and out-of-equilibrium dynamics. So this is clear when you look at training dynamics, for example, to solve nonlinear regression tasks. And it's even more difficult when you have training and generative dynamics that couple together, because in this case, you not only have the dynamics of the weights of the network, but the dynamics of the weight of the weights of the network is going to control the dynamics of the model, the generative dynamics. And so, I mean, we don't have a very good theory to understand high-dimensional nonlinear dynamical systems. And so, what I'd like to do in this talk is to tell you two results. So the first part of the talk, I will basically address the problem of training dynamics, so no generative dynamics. And what I want to do is to try to understand how it's possible that feature learning emerge in overparametrized settings. And what I will do is to consider a simple case that is the one of overparametrized two-layer neural networks. And the main message that I would like to convey is that in this simple case, we can show that feature learning and overfitting coexist in these models, but they live on different time scales during training dynamics. And the time scale is basically controlled either by the network size or the number of data points. Okay, and this is the result that is contained in this paper. And the second part of the talk will be more on try to define exactly solvable models where I can study training and inference dynamics together. And the idea will be to use de facto models of recurrent neural networks and try to study learning there. So this makes a bridge with, let's say, computational neuroscience. Okay, so what I want to do now is just to study training dynamics. And okay, I will consider a very simple nonlinear regression task. So I have some training data. This is composed by vectors in d dimension. This is large. And each of these data points has some attribute, some response, yi, that I will assume is just a real variable. And okay, you can generalize to vectors, but that's not very important. And there is some structure that there is in this data, and you want to capture this structure via a parametric model. So parametric model is just a fitting function. It's a neural network. It depends on a set of parameters. These are the weights of the network that live in some high-dimensional space. And the idea is that you want to fit these parameters to best capture the structure that you have in the training data. And how do you do? Well, you define, you try to solve an empirical risk minimization problem. So you define the empirical risk. It's just a measure of how well the network perform on training data. And then you try to minimize it. And in general, the parametric model that you use is a nonlinear function. And so the empirical risk is a high-dimensional non-convex cost function. So there are not so many open-purpose algorithms that we know that work in these settings. And basically, we are stuck to gradient descent, gradient flow, or stochastic versions of it. And therefore, I mean, this is some high-dimensional nonlinear dynamics. It's very hard to understand what are the attractors of these dynamics, and therefore it's hard to give theoretical guarantees about the performances of the corresponding model. And this is a technical problem. There is a conceptual problem, as I was mentioning before, that is the fact that all these things is done in regimes that are very far from classical statistical learning theory, meaning that you train these models in situations in which the number of training data points is huge, the number of parameters is huge, and in many cases, these two numbers are close to each other. And actually, in many cases, this is the example of this paper in 2012, the number of parameters is larger than the number of training data points, and this is what is referred to as overparametrization. So what's the problem with overparametrization? Well, the problem is that if you are in this situation, you can think that the attractors of this dynamics are configurations of the weights such that the empirical risk is zero. So what does it mean? It means that you can find interpolators. So what are interpolators? These are just configurations of the weights that perfectly interpolate your training data. And if your training data is noisy, well, you are overfitting the noise. So if you believe like standard assumption in classical statistical learning theory, you would say, okay, I have a model that is super expressive that can fit the noise, so I don't expect that it's learning the features. And what is found empirically, these are experiments, what is found is that basically these overparametrized models are so expressive that can fit even pure noise data, but when you train them on meaningful data, they learn some good internal representations. And the question is how it's possible. So this is, I think, really conceptual. And in order to understand this question, we need to understand training dynamics. Okay, so people have thought a lot about this, and I think that it's fair to say that we have two limiting theories of training dynamics. So the first one is the neural tangent kernel. So it's basically a set of limiting initial conditions for the network such that you can prove that when you start a gradient descent, very nearby, you have an interpolator. So the weights of the network move very little. And if they move very little, well, basically, I can expand my fitting function at linear order. And so I get back basically a linear model, right? So the NTK theory tells you that you can have regimes in which it's very easy to find interpolators, even in this high-dimensional non-convex setting. But the problem is that the model that is working there, it's a linear model. So you don't expect that it capture feature learning. It doesn't work by doing feature learning. So the other theory is feature learning theory. It's a set of limiting situations in which basically you can replace the empirical risk. So this is this high-dimensional convex cost function with the population loss. So what is the population loss? Is the limit of infinite number of training data. So if I have an infinite number of data, this cost function can become much smoother. It can have few local minima, and these local minima can correspond to configurations of the network that have captured some latent structure of the data. So this is nice because it tells you that, I mean, if you are in this limit, you can have this nonlinear phenomenon where the weights of the network align with the structure of the data. But of course, the problem is that given that you are in this situation in which you assume that you have an infinite amount of training data, if the training data is noisy, well, you cannot capture overfitting, right? So it's a limiting situation in which you can capture feature learning, but no overfitting. And so somehow we have two theories that work in different limiting conditions. They don't talk to each other. And so the question is, can we have a setting in which we can address both overfitting and feature learning, and that is more realistic?
Well, could you explain what you mean by the population loss?
So if I take, instead of taking just n data points, so the number of data points is finite, you take just the limit in which this is infinite. Okay, so you're just taking the expectation over, so you take the empirical risk, and you're just taking the expectation over the distribution of data. Okay.
But that's the definition of the generalization error.
Yes,
and
yes.
you don't have access to it. You can make an algorithm.
Exactly. So this is a kind of limiting situation in which if you, and I will show that, I mean, when you do gradient descent at finite number of data in some dynamic regime, this is what happens. Okay, so we studied this problem in the context of overparametrized two-layer neural networks. So these are very simple fitting functions that work like this. So you have some input data, and then what you do is that you multiply by a set of first-layer weights. These are the weights of M neurons. So you have M hidden neurons. Then you apply a nonlinear function, and then you take the weighted average. And so we assume that we have some first-layer weights that are normalized in this way. The second layer weights, we assume that they're just scalar variables not regularized. We have M hidden neurons, and this is going to be an important parameter. And we assume that we have a data set of small n training data points. And we want to work at fixed overparametrization ratio. So that's the number of trained data points divided by the leading order of the number of parameters that is in the network. And I will assume that this thing is smaller than 1. So I'm always overparametrized.
Excuse me.
Yes.
But each data point is d-dimensional. So
Yeah.
the numerator is not n, is nd.
No. This is n. Okay, so what is the distribution of data that we want to that we can use? So this is a very simple model where you can really study feature learning. Okay, so this is called single index model. And what is this data distribution? So I assume that these vector xi's are Gaussian. And I have a set of random Gaussian variables, epsilon I, that this will be just the noise that is in my data. And then the responses, yi, are just this random noise plus a nonlinear function phi computed in the scalar product between xi and some fixed vector w star. So if I look at this process, well, basically the yi is going to be correlated with xi through this feature vector w star. So somehow learning here, learning the internal representation is basically finding back what is this particular direction w star. So it's a very simple model where I can really study feature learning. And so the question we want to understand is what is the dynamics of the test and train error? When does overfitting takes place during train dynamics? And okay, so we study gradient flow. So we define the empirical risk, that's just the square loss. And we run gradient flow, okay? So this is just a very simple algorithm. And we start from some initial condition that is basically random. And we want to compute what is the dynamics of the test error, okay? So how well I'm performing on new data points. And okay, so how do we study this? So we use dynamical mean field theory. So we can track the dynamics in the asymptotic limit in which the number of data points and the input dimension go to infinity at a fixed ratio. So we can derive a set of dynamical mean field theory equations in this limit, and this is basically an extension of some work that I did together with Persia Kamali. And then what we did with Andrea is basically study the limit in which we take the large width of the network. Okay, so we want to study what happens when the network becomes very large, but at fixed overparametrization ratio. So I want to be always overparametrized. And what will happen is that the dynamics will take place on several time scales. And so it's crucial that you need to control what happens at a given time scale given the previous one. So you need to build some machinery to make some coarse graining of dynamics. And this is kind of an RG analysis of these DMFT equations in this large width limit.
But you just have 2 time scales, or do you have multiple time scales coming in?
So you can have like 3 time scales. So the case that I will show is just 2 time scale. But for example, in one case where you get clearly 3 time scales is if you take, for example, pure noise data, typically there you can have 3 time scales. And okay, there are matching regimes, and these matching regimes are controlled by some spin glass models. So I can tell you later. But for the case that I will show, it's just 2 time scales. Okay, so I will not tell you the details, but the result is this one. So this is what we get. So this is so in purple it's the train error, in blue it's the test error as a function of time, and this happens when I take the large width limit. So what happens in this limit is that we have 2 time scales. So for time scales of order 1, basically the train error is close to the test error, and on long time scales, basically you learn the latent structure of data. So you do feature learning. And actually, you do feature learning for a long time. So for a long time, basically, during training dynamics, the network is stuck on a configuration in which you have basically learned the internal structure of data. And in this regime, this feature learning theory is correct. And then only at long time scales that scale either as the width of the network or as the number of data, we are in this proportional regime. So only on this time scale you enter the overfitting regime where the train error goes down. So you interpolate the noise that you have in the data. and the test error moves up. And correspondingly, you unlearn the latent structure that you have in the data distribution. And so the basic thing here is that there is a kind of coexistence of feature learning and overfitting. And the coexistence is controlled by a time scale that is basically proportional to the width of the network.
What is the role of the function phi here?
So the function phi, we assume it's generic. It has, so for example, there is no information exponent.
That's what I'm asking.
Yeah, there is no information exponent, which I think it's kind of generic situation. Sorry?
It's finite.
So here I'm just saying this is a kind of asymptotic plot in the sense that this is true for large M. So for large M, this thing, okay. So this thing is large and it scales like M, okay?
But you are interested in alpha positive, not alpha which goes to 0.
So I'm always at alpha positive and fixed. So alpha is order 1 and smaller than 1. So I take the scaling limit in such a way that alpha stays order 1 and smaller than 1.
Alpha was N over D?
N over M times D.
M times D.
Yeah.
So I guess this is training divided by test error. So why is that so bright?
What do you mean? No, it's training and test. Sorry, it's not training divided by test. It's training and test error.
Okay.
So this is train and this is test.
Okay, sorry.
Sorry. Okay, so why I think it's interesting? I think it's interesting because if you think about some naive scenario to explain this, what you could say is that, okay, so these things are overparametrized, so the train error is going to do something like this, and the test error is going to have a minimum somewhere, and maybe you are just looking for this minimum. So I think this is kind of impossible, right? Because the space of parameters is so large that you are not going to look for this. But if you have this scenario, basically you have a large time scale where whatever you do to your training dynamics, if you stop training dynamics there, you get a very good network, okay? And this is a robust mechanism for early stopping to work. So that's what people do every day. And okay, so what is the mechanism for this separation of time scale? Well, basically it's a slow increase of the function complexity. So here, what happens is that you start from a neural network that has a small complexity. So the fitting function has small complexity. And here the complexity is basically the L1 norm of the second layer weights. So this is Rademacher complexity. And then what happens is that on time scales of order 1, so much smaller than M, this complexity stays small and test and train error are close to each other. And then you need to reach time scales that are of order M in such a way that the complexity of the fitting function has grown sufficiently so that you can overfit the noise. And basically, this is a kind of mechanism that is very generic, right? So there is nothing that I'm using here about the structure of the dynamical equations of the weights that is driving this result. So this is really a kind of generic picture. Okay, so this is what I wanted to tell you about training dynamics. And now I want to add to that inference dynamics. Yes.
Maybe this is what you meant by coarse grain or something, but your initial conditions for the long time scale limit are something like that's the output of the short time scale?
Yes.
Limit,
Yes.
But then there's all the intermediate time scale. I guess that.
What do you mean, the intermediate time scale? So here, so this regime?
Yeah. Well, what initial conditions do you put in the like long time asymptotic?
Well, you have some, so you need to coarse grain the dynamics and just construct some observables that enter and are the relevant one in the long time regime.
And they're the long time limit of the short time dynamic.
So I can make an example maybe at the end. So where I can show some spin glass landscape back because there will be no spin glass landscape here, but there is. It's there. Deep in. Yes. Sorry.
This all in the information theoretically solvable regime where the sample size are enough.
Yeah. So here the question is not about if I can learn this function efficiently with a smaller network. So I want to use this as a case in which the function that I want to learn is very simple, but I use like a very complicated network, which is I mean, what you typically could do, right? So you have some simple tasks, and then you want to learn them via some very complicated architecture, some very complicated function. So that's the scope of this thing. So I'm not claiming that this is an efficient way to learn single index data. That's not the point of the work. Yes.
So the idea of looking at complexity seems quite appealing. Why look only at the second layer? And does it matter how you initialize the system?
Yeah, it matters how you initialize. So all this works if you initialize the second layer to L1 norm that is of order 1. So if you scale up the second layer, you can skip this feature learning phase. Okay, so if the initialization of the second layer is too large, then the initial complexity is too large, and you are already in the overfitting regime. So you can skip this thing. So I can come back to that at the end if you want. Okay, so now what I want to do is to add inference dynamics on this, which is generative dynamics. And one way to do it smoothly is try to understand how I can go beyond two-layer neural networks and to model something that is multi-layer. And one way to think about it is think about these multi-layer networks as kind of dynamical systems that basically transform input into outputs. And here the index of the layer becomes a time index. Okay? And so this is the perspective of neural ordinary differential equations, in which you can model these objects as kind of discrete time dynamical systems. And the weights here depend on time because they depend on the layer index. And basically what you are trying to do is to find the weights that basically transform input into output in a kind of controlled way. And okay, you can have discrete time dynamical system, but there are some situations in which you can also take the continuous time limit. So this is the case, for example, of residual neural networks, or whenever you have some skip connection, this is basically a continuous time dynamical system. And so you have some dynamical variables, that's the output of the network at layer T. You have some control variables that are the weights. These are the weights of time T at layer T, and they live in some high dimensional space. And then you want to train this via some end-to-end training. So this is a very complicated situation. You can study a simplified problem. So there are many generalizations of this setting. And one simple generalization, it's a simplification of the problem, is the case in which the weights are time independent, right? So I can try to study. So it's a high dimensional nonlinear dynamical system that is controlled by a set of weights that are high dimensional too. And so can I study training dynamics in this situation? And a much more complicated model.
How are you training it if the weights are fixed?
Sorry?
How are you training it if the weights are fixed?
So this would correspond a kind of one-layer neural network for a very complicated activation function that is induced by the dynamics of the network. But so the weights are not fixed. The weights, I want to learn them from this data set. So I'm given a data set. For example, this is input-output of the dynamical system at time 0, time t.
Independent of the layer.
Exactly.
Okay.
The theta are independent of the layer, but I can learn them. So I have two dynamics. One is the dynamics of the dynamical system, and the other one is the adaptive dynamics of the weights. And okay, so this is a simple case. It's still very interesting. A much more complicated case is the one of transformers. So one way to model this is through some nonlinear dynamical system that has some memory. So these transformers act on some context of some length. So you have a set of high-dimensional tokens that are processed in the transformer blocks. And so you need to add some memory to your dynamical system, and you will have a set of weights that control feature learning, a set of weights that control attention, and okay, so you can make a complicated model. And so you can have a class of high-dimensional nonlinear dynamical systems that are controlled. So this is optimal control, but it's optimal control in a regime in which the number of control variables, these are the weights, is very large. And so the question is, do we have tractable models for this? And what are the desiderata for these models? Well, for inference dynamics, what you want is to consider some kind of high-dimensional dynamical system. Think about token dynamics. And this high-dimensional dynamical system is typically nonlinear because the transformations that you do on tokens are nonlinear. And the vector force field that basically is driving these dynamics is non-conservative. So if you think about the attention block, it's not following any gradient of any loss. And for training dynamics, well, again, we have high-dimensional weights. The dynamics is going to be nonlinear. And for AI setting, where you typically train the system by minimizing some training objective, well, the vector force field is conservative somehow. So you are taking the gradient of some loss. Maybe you add some noise. But for example, if you think about neuroscience, this also has to be changed, right? Because we believe that probably there is no back propagation as we know it in artificial intelligence in the brain. And so what are good models? So a possible choice would be to use models in computational neuroscience. In particular, to study inference dynamics, there are two types of models. First, you can have Hopfield models. And the problem is that Hopfield models typically are driven by a conservative vector field. So these are associative memories. There is a Lyapunov function that is optimized during dynamics. So this is different from what we want here because we wanted to have something that is it's not conservative. And so the other option is to consider recurrent neural networks. And in statistical physics, there is, the main model of recurrent neural networks was studied in the 80s by Sompolinsky, Crisant, and Summers. So it's a model of neurons interacting in a nonlinear way.
Pierfrancesco.
Yes. Sorry.
Oh, I was just confused. In the previous slide, can you say real quick, the training dynamics, I understand that's the dynamics of setting theta.
Yeah.
What are the inference dynamics?
So this is the dynamics of the tokens. So if you think about the multi-layered network, is the dynamics across layers.
And when you say desiderata, that's desiderata from
Yeah, it's just
to understand that, or
if you take any transformer, whatever architecture it is, and you think about in terms of dynamical system, in general, you have this desiderata. So it's a high-dimensional, nonlinear, and the vector force field is non-conservative. So this is, if you take a transformer, the autoregressive dynamics is not driven by any conservative vector field. So it's very basic properties of these dynamical systems that we want to embed. And okay, so we have this Sompolinsky-Crisanti-Summers model. It's a model of random recurrent neural networks. So you have a bunch of neurons. To each neuron, you attach a variable. It's a real variable. So you have n neurons, and you have these dynamics. And you have a set of couplings, Jij, that basically tune the synapses between different neurons. And these couplings are in general non-symmetric. So this dynamics is not controlled by any Lyapunov function. And okay, so people have studied this dynamical system a lot, and have done all sorts of things in computational neuroscience. But the problem is that as soon as you want to analyze it, okay, you can analyze for example, in this setting, which maybe the Jij are random, but as soon as you want to study learning, it's kind of hard. And so what we decided to do with this is some stream of works with Samantha Fournier is to try to take the following perspective, which is, okay, let's simplify these dynamics. Let's take a simple model. The simplest it is, the better. And it has to be so simple that I can study training and inference together. And the type of dynamical systems that we consider are very simple, and people also studied them. So imagine that you have a vector x. It's a vector in R to the d, and d is large. So these are high-dimensional token dynamics. And you have some term here that confines the dynamics in such a way that this vector x doesn't explode. And then, for example, you want to mimic the fact that you have some baseline of activity that is a kind of random part of the dynamics. Okay, and so this vector field here is a kind of random vector field that is Gaussian and it has some statistics. And the statistics is such that this function g is nonlinear, so that the underlying model is not integrable. And then you can add some terms that encode for plasticity and some input, sensory input. And what we have done is basically try to show that this model has exactly the same phenomenology of this model.
So you put the spin glass back in.
It's not a spin glass,
No,
this.
but the random Gaussian force when the
It's
isotropic, it is a spin glass.
it's not a spin glass, there is no landscape here.
There is what?
There is no landscape.
gradient?
It's not the gradient of any loss. There is no spin glass. No spin glass. There is no Lyapunov
The
function.
Gaussian isotropic field.
It's a vector field. It's not a function. It's a vector field.
Function, I see again.
Okay, so I mean, you can show that basically this thing has the same properties as this. For example, it has some fixed point to chaotic transition, the same type that Valentina was discussing. And here actually it's nice because you can even compute the maximal Lyapunov exponent explicitly in the chaotic phase. One thing that people in neuroscience, in computational neuroscience have done is to train this dynamical system to perform some motor task. And actually we can do exactly the same in this dynamical system with advantage that the algorithm that people developed, and this was done in a very influential paper by Susil and Abbott, is kind of heuristic. And here we can do a theory in high dimension for this. And the last thing that we did is basically...
Can you just, on that equate the Z of T and the...
I think the time is... So what you want to do in this task is basically you take your dynamical system, you add an output neuron, think about motor neuron. So you want that this neuron fires a periodic signal. And so you want to train these weights such that this neuron fires a periodic signal. So they have this algorithm that is called FORCE. It's first order reduce and control error.
DOT is given and you're training the WIs.
Yeah, so the output of DOT, you fix them, you fix it, this is a desiderata, and then you want to train these blue weights. So we can do the same thing in this like abstract model. We have exactly the same training phases, and we can do the analysis via dynamical mean field theory. So we can study, for example, what is the stability of the attractor where you land after a certain number of training epochs. Okay, and the last thing that we did, and then I will wrap up, is that we can use actually this dynamical system to plant limit cycles. So this is something that people have tried a lot to do. And we have a very simple model in which there is basically no learning, just plasticity. So you have some plastic term, some periodic input drive, and you can show that there is a phase in the phase diagram where after some stimulation phase, the system lands on a limit cycle. So basically you planted a continuous attractor in the model. Okay, so this is just to say this dynamical system has the same properties as the standard models. But the thing is that now you can add control variables and you can study training dynamics there. And the easiest way to do is basically you add some control variables here. So you define a kind of teacher-student scenario in which you have a teacher dynamical system that has to be fitted by a student one. And the idea is that, so you will have a set of variables theta that you're trying to adjust. So you have inference dynamics and you can study also training dynamics. And okay, how do you train this? Well, basically you do the adjoint method. So you transform your trained objective into kind of Lagrangian, where you enforce basically the inference dynamics, and you do this via some conjugate field. So this is basically a large deviation theory seen in a completely different way. It's optimal control. And this conjugate field basically encodes back propagation. So it's really a way to see back propagation. And then once you have the solution of these equations, you can update the weights. So all these are dynamical systems in a dimension. And for this particular class of models, we can study them via dynamical mean field theory. And one comment is that actually these dynamics for back propagation can be deformed. So you can try to adjust the dynamics to satisfy some biological constraints. And okay, so you can derive some effective processes of the DMFT, and you can study learning. So these are learning curves where you show that this online learning setting basically succeeds. Okay, so there are many generalizations, and okay, one generalization is that we can go to the empirical risk and we can extend this dynamical decoupling to generative models. So this dynamical decoupling of feature learning and overfitting basically extends to the decoupling of generalization and memorization in generative models. And okay, so I think I can stop here. I'm sorry.
And the last slide you didn't show us, and then you can prove theorems by automatic.
This is going to be done automatically, let's say, proving theorems.
Okay, maybe we can take one question, and then we have a break, and then the next. Okay, one question.
Can you store more complicated objects than limit cycles in the network, or like more limit cycles?
No. So for the moment, it's just, I mean, even limit cycles, they are kind of hard to learn. So for the moment, what we are trying to do is so here we can store just one limit cycle via this plasticity rule, and basically this plasticity is kind of a baby version of the context transformer, so it allows you to integrate over long time scales. And what we are trying to do is to plant more limit cycles.
Yes.
So, for example, you have some selection signal here that allows you to switch from one limit cycle to the other. And maybe we could have like two limit cycles that maybe encode for some two-dimensional coordinates when you navigate space. So the idea is to try to use this for computational tasks. Okay. But for the moment, we managed to get these limit cycles. Yeah. Thank you.
Okay, let's thank the speaker again, and